for the invitation. This will be kind of a change in topic. It will still involve flat bands, correlations, and the external magnetic field. And since there were no talks on twisted bilayer graphene, I will start with a fairly basic introduction to this problem. I will tell you about the single particle and many body effects in the absence of the magnetic field. This is some progress that has appeared in this field since 2018. And then I will talk about the main part, which is the effects of the finite magnetic field, in particular in the strong coupling regime. I will tell you about a new approach to the Hofstadter problem. If you have a band which is isolated from the rest of the spectrum, that band may or may not be topological. It is an interesting question. How does this band behave in the presence of an external magnetic field? Whether you have interactions or not. And we would like to be able to describe that regardless of whether this band is topological. And I will show you a way to project onto such a narrow band at finite magnetic field. I will apply this to the twisted bilayer graphene at strong coupling, and then connect this to the new approach to this problem, which was advanced a couple of years ago by Andrei Bernevik and Jida Song, namely topological heavy fermion model. And I will take this model and show you how to study it at finite external magnetic field. And we'll see that the results from this approach will qualitatively explain the results from the approach which doesn't know anything about the topological heavy fermion description. I will not be able to talk about this last part. So here are my collaborators. Jian Kang used to be a postdoc at the Magnet Lab. He's now on a faculty at Shanghai Tech. Xiaoyu Wang is a postdoc at the Magnet Lab, and Keshav Singh is a second-year grad student at the Mag Lab. And we were fortunate to collaborate with Andrei Bernevik's group. Aaron is a postdoc at Princeton, and Jonah is a student. Okay, so imagine you take two layers of honeycomb lattice, you put them on top of each other, and then you twist them by some small angle. This is not to scale. And we're going to be thinking about these angles to be of the order of 1 degree. Then there's clearly a new pattern that emerges at length scales which is much longer than the underlying carbon-carbon distance. This is this triangular moire pattern that you can clearly see by your eyes. And the typical length scales that we will be interested in when applying to the experiments is this length to be of order 14 nanometers. It, of course, will go up as the angle is decreased and roughly as 1 over the angle. Okay, so clearly this is a much, much longer length scale than the carbon-carbon distance. And now, if the system is clean enough, the famous Dirac particles of each graphene layer will be scattered by this periodic potential. They will form new mini-bands. And because the new unit cell is so large, you can now use the field effect transistor to fill or empty these mini-bands. And you can do that without, you can do this reversibly. Okay, so how do we think about the band structure? In this cartoon, let's imagine for a moment that the two layers are completely decoupled from each other. So there's no possibility for the electrons to hop from the top layer to the bottom layer. Well, then the problem is easy. We have the Brillouin zone from the top layer, which is marked by this blue large hexagon, which has its Dirac point in this corner. Of course, there's a time-averse partner in the other corner. And then the bottom layer, which is twisted relative to it, will have its Brillouin zone, which is twisted by this angle theta. And therefore, the corner of that Brillouin zone will fold onto a different point. And now, if we were to take a cut in the momentum space between these 2 points, what we will see is a Dirac cone of the first layer intersecting the Dirac cone of the second layer. And that intersection will happen at an energy which is set by the slope, which is just the Fermi velocity, and then half the distance in momentum space between these two Dirac points. So that's one energy scale in the problem. Now imagine that we turn back on the interlayer tunneling. If there's a finite interlayer tunneling, then this level crossing will turn into level avoidance. And there will be a gap that opens up over here and over here. And the energy scale associated with that now will be fixed by chemistry, although in principle you can change that by pressure. We are going to call that energy scale W. And now imagine that, let's say you hold the twist angle fixed and you start increasing W, then you see this band pushes against this one, and so it's pushing it from the top. This band is pushing against this one, it's pushing it from the bottom. And so when this W is of the order of this energy scale, set by half the distance between the two Dirac points times the slope, you have a chance of flattening out this band. It's not at all obvious that this will happen, but at least there is a chance. And turns out that this estimate is actually pretty good, as I will show you in just a second, when this is not quite order 1, but slightly different from it. So the ratio of W to VF delta K is actually something like 0.6 as opposed to 0.5. You will indeed find the famous flat bands. As I said, the denominator in this formula, so the distance between these two Dirac points, is controlled by the twist angle. And the numerator in this formula is controlled by the pressure. Okay. So we can do it in a slightly more sophisticated way. We can expand in gradients around the high symmetry points in the Brillouin zone, and to first order gradient expansion, arrive at the following effective Hamiltonian. This is a 4x4 differential operator which acts within a specific valley for specific spin projection. This 2x2 describes the massless Dirac particle of the top layer. The 2x2, the two components here are the sublattice on the A sublattice and the B sublattice of the top layer. This is, of course, the massless Dirac particle of the bottom layer, and then there is the interlayer tunneling. This itself is a 2x2 matrix, which is parametrized by a tunneling through the AA region, the regions where the two layers are perfectly stacked on top of each other. And then there is a second energy scale associated with the tunneling through the AB region. They're not exactly the same. We're going to keep them as free parameters in this model. In particular, their ratio will be a free parameter in our model. Okay, so and then these small q's that are sitting here, they just come from the twist. They are this mini Brillouin zone for the Moret is parameterized by these vectors. All right, so if we take this model, this has a discrete translational symmetry. We can then numerically diagonalize this with many, many, many plane waves until we converge. The result will look something like this. So there will be a mini Brillouin zone. This is the center of that mini Brillouin zone. This is the corner. This is the other corner. This is the gamma point. And the movie that will run on the right is the band structure one obtains from this continuum model for a specific valley. The other valley is related trivially by time reversal symmetry. It starts with the twist angle of 3 degrees, which is too far from matching those two energy scales which I mentioned, the level repulsion and the energy of the level crossing. So the bands start out fairly broad. Okay? The dispersion is plotted along this specific cut in this mini Brillouin zone. And in this movie, the angle will now decrease towards the magic angle. Now, of course, as the angle decreases, the Moret length scale grows, and so the Brillouin zone should shrink, but I will continuously rescale it such that this axis is staying fixed. And so as this angle decreases, you see the levels are effectively pushing against each other more strongly, and eventually, when this angle is about 1.1 degrees, the bands become extremely narrow, right around now, and then they broaden again. Okay, so that's the famous calculation from more than 10 years ago. That was the prediction. And of course, the great breakthrough came from the experiments in Pablo Jarillo Herrero's group at MIT, where they took devices which were twisted too close to the magic angle, 1.16 degrees, and found that as they changed the carrier concentration, now remember there were 2 bands per valley per spin. That means that if we include the valley, we need to multiply by 2 and spin by 4. And so as a result, there will be 8 electrons per unit cell that you need to go from the narrow bands being completely empty to being completely filled. So at this carrier concentration, they find that the system, this is a 2-terminal conductance, the system is insulating. That's when the narrow band is empty. Here, the narrow band is completely full. It's also insulating. So that's what's expected from the non-interacting theory. And the new surprising thing was that as you sweep between these 2 fillings, roughly around, well, at 2 holes relative to the charge neutrality point per Moray unit cell, or 2 electrons, they saw signatures of insulation. And remarkably, next to that insulating state, they saw superconductivity. There was also a signature at 3 electrons per unit cell, so odd filling of this narrow band. And of course, this then exploded into a big field where we're still trying to understand the nature of these states and the nature of the superconductors. So these are the early experiments. Let me see, how do I go back? So in this particular case, if you see this axis actually, in this original Nature paper, the axis actually dropped at 0.1. If you were to go below this, it actually becomes superconducting. Now, the current understanding of that is that it's actually inhomogeneous. The twist angle was not fully homogeneous. And so, in fact, the superconductor just percolated through this. Now, the more modern reincarnation of this now actually see it a lot better and cleaner. And in fact, it looks like the superconductivity is probably only on the away from the charge neutrality point side. All right. Now, but even in the original experiment, what was seen is that, well, first of all, it's quite remarkable that if you apply an external magnetic field only of the order of few Tesla, you are already pretty quickly deep in the quantum regime. There are only few Landau levels which get populated. And this is the Landau fan, which originates from the charge neutrality point. And here is the reset. This is the nu equal to -2. So we have 2 holes relative to the charge neutrality point per Moray unit cell. And you see that the Landau fan is pointing away from the charge neutrality point. So I'll come back to this. Notice there's no Landau fan pointing towards the charge neutrality point from nu equal to -2. They also saw, they also measured the Shubnikov-de-Haas frequency. It grows as you increase the density away from the charge neutrality point, as Fermi surfaces are growing. And then there's a reset. And again, it grows starting from nu equal to -2. And similarly, from the temperature dependence of the Shubnikov-de-Haas frequencies, they extracted the effective masses that grows, resets, and it starts from low mass on this side. And I will come back to this as well. All right, this is a more recent version of these experiments from Andrea Young's group. Again, you see that this is the charge neutrality point. This is the filling factor -2. This is the filling factor -1. Again, the Landau fans are clearly pointing away from the charge neutrality point, particularly here and even at nu equal to -3. And in this graph here, they're plotting the whole density as they are moving towards the bottom of the narrow band. And you see at -2, there is a reset. It comes back and almost fully resets here as well. All right. So, okay, so that's one important part of the story. As the band is narrowed near the magic angle, strong correlation physics is observed experimentally. Now, the second important part of this is that the narrow band is topologically non-trivial, particularly if the small the intervalley scattering at the single particle level is ignored. So, one way to test for the topology of these two narrow bands. Now, notice the system has a C2T symmetry, therefore it will not have any finite Chern numbers, okay? But it can still be topological in the similar sense that the 2D topological insulators are topological without having finite Chern numbers. So one way to see that is to diagonalize the projected position operator in the subspace of these narrow bands. Sometimes these are called Wilson loops. And because there are two bands, we're going to find two eigenvalues of this, projected position operator. And this is the position operator in the x direction. So, of course, there's a perpendicular direction along which we still have discrete translation symmetry. And so we can label all of these two eigenvalues as a function with a continuous quantum number that has to do with the translation symmetry in the perpendicular direction. And now we can ask, will these, another way to think about it is that there are two wave functions that you can build out of the two narrow bands, which are localized in one direction, but they're Bloch extended in the other direction. They're also called hybrid Wannier states. Now, this is what they look like in real space. And we can ask what will happen to the center of these hybrid Wannier states as we increase this good quantum number, this momentum along this direction. So if this was a trivial system, what would happen is, topologically trivial system, what would happen is that this center would basically sit at the same point. It may oscillate back and forth, but it will eventually return to the same position. Now, imagine this was a Landau level for just a second. If this was a Landau level, and as you increase, let's say in the Landau gauge, you increase the momentum along the good, along the translationally symmetric direction, what would happen is that the Landau level wave function would drift, let's say, from left to right. And that's one way to detect its topology. And so, in fact, that's precisely what happens here. One of these will drift from right to left. That's the red one. And the other one, the other partner, will drift from left to right. And you can actually see that the distributions, the full distributions are shown here. They're still peaked at this triangular AA lattice, but the centers of these distributions are indeed winding. And so that's one way to detect the fact that this narrow band can really be decomposed into two topological states. You can find a proper linear combination of them, and then one of those linear combinations will behave as a Chern plus, and the other as a Chern minus band. And so this is an interesting new aspect of this problem. We have narrow bands. Clearly, the interactions play an important role, but at the same time, these narrow bands are topological. Okay? All right. And so now the question is, how do we think about the interactions within these narrow bands? In principle, there are many, many, many bands in this problem. If we were to solve the model that I just showed you, let's say numerically, we're going to find that, of course, the large Brillouin zone of the graphene will fold into tiny Brillouin zone, and that will create thousands of mini bands. We're only interested in the ones which are highlighted in this region of energy. So what we would like to do is we would like to come up with some effective Hamiltonian that acts only in the subspace of these narrow bands. Now, if the system has a particle-Hall symmetry, there's a fairly rigorous way of approaching this. We can set up a renormalization group procedure in which we integrate out the high-energy modes shell by shell in the Wilsonian sense, and eventually obtain the effective Hamiltonian in the narrow band. For those who are interested in the technical details of this, the key idea is that in this, to split the energy window into three different regions. So one is the energy window between roughly the lattice scale, so Fermi velocity divided by approximately the carbon-carbon distance, and then the energy scale set by the interlayer tunneling. So this is of order 100 millivolts. This is of order volts. And then in this energy window, the Coulomb interaction turns out to be perturbative, and so is the interlayer tunneling. So despite the fact that there are thousands of bands here and the problem looks almost impossible, you can actually set up an analytic calculation for the flow of various parameters in the effective Hamiltonian that I showed you, and integrate out thousands of bands analytically. Then there's a stage 2, which is below the energy scale where the interlayer tunneling becomes important. So there we cannot treat the interlayer tunneling perturbatively, but the Coulomb interaction is still perturbative because we have this gap to the remote bands. So in this case, where we have anything between 20 and, let's say, 40 bands left, we can then integrate these bands shell by shell, so band by band, renormalize the self-energy and the interaction, and numerically, and eventually arrive at a model within just the narrow bands. So this is our procedure for systematically projecting the Coulomb interactions onto these remaining narrow bands. When this is done on the model that I just showed you, what we find is the following. The projected Coulomb interaction has the following form. It is a density fluctuation operator, which is itself projected onto the wave functions of this narrow band, with the interaction which is which depends on your starting interactions, but think of this as, let's say, gate-screened Coulomb interaction. And then the residual kinetic energy we find to be small compared to this projected Coulomb interaction. Okay? So then, once we are done removing perturbatively in the Coulomb interaction all these remote bands, we would then need to solve this problem in strong coupling. First solve the projected Coulomb interaction problem, and then bring back the kinetic energy perturbatively. Now, there's an important symmetry that is present, approximate symmetry, which is present in this problem, which was pointed out by Jida Song and Andrei Bernevik and Leon Balance's groups. This symmetry at the non-interacting level allows you to relate wave functions, full block wave functions, in band N and crystal momentum K to the exact wave function in its negative energy partner at the opposite momentum. So this K will be minus K, so you can relate the wave function at this minus K to the wave function at K. Okay? The Pauli matrix, the second Pauli matrix mu acts in the layer space, and then this Pauli matrix X, the first Pauli matrix, acts in the sublattice space. Okay, now it's not obvious, but this symmetry allows us to take the density operator and generically show that as long as we ignore the large wave vector scattering between the two valleys and only allow small wave vector scattering within the valleys, the off-diagonal terms vanish, which is trivial because those are just connecting the two valleys. But the blocks within the valley are actually related to each other. They are not independent. So nominally, the only thing that connects the two valleys would be at the same position R would be the time reversal symmetry. So you would expect this block to be just complex conjugate of this block, but this symmetry allows you to, in fact, relate them without complex conjugation. And now, for any position, this 4x4 matrix now commutes with the following four matrices. So trivially commutes with an identity, and the tau z in the valley space. So that's because you simply do not couple the two valleys. So that's simple. You have what this means is that you have independent spin rotations within each valley. But remarkably, you can also rotate between the valleys. Notice this is not the symmetry of the non-interacting Hamiltonian, but the projected density operator actually enjoys this larger symmetry. And so, in fact, the projected Coulomb interaction, the term that I argued dominates, has a higher symmetry than the kinetic energy, which is dropped because the band is narrow at first order. And this, in fact, has a global U4 symmetry, which allows us to rotate not just between the spins, or for example, spins within each valley, which would be U2 cross U2, but in fact allows us to rotate between spin and valley in this continuous fashion. Okay, now in the so-called chiral limit, if you were to drop the interlayer tunneling through the AA region, this symmetry, which is a bit of an artificial limit, but nevertheless is discussed quite a bit in this field, this symmetry is even larger. You can make independent U4 rotations in each churn sector. But in the more realistic case, you can only perform rotations. If you perform a U4 rotation in one churn sector, the U4 rotation in the other churn sector follows. It's not independent. Okay. So now we understand what our effective Hamiltonian is in this case, and we know its symmetries. And so there are certain exact statements one can make about this Hamiltonian. So in particular, at charge neutrality point, if you can find a many-body state which is annihilated by this density fluctuation operator, then you found a ground state because the interaction is positive semi-definite. And it turns out that these states are easy to form. For example, if you were to take a fully valley polarized state, that will do the job. It will be annihilated by the density fluctuation operator. But because of this larger U4 symmetry, you can rotate that valley polarized state into other interesting states, for example, intervalley coherent states, etc. And all of them at this level will be degenerate. Now, at even integer filling, we can find exact eigenstates of this density fluctuation operator. And it was shown numerically in this series of papers that these many-body eigenstates of the density fluctuation operator are also the ground states for a large range of parameters for this Hamiltonian. At odd integer filling, it's harder, and in particular, you have to resort to numerics. But if you are in this special chiral limit, then the sublattice is perfectly polarized, and it turns out that churn states are ground states of this Hamiltonian. Anyway, the upshot of this story is then generalized spin valley ferromagnets are favored by the projected Coulomb interaction. Okay. Now, this theory in this limit then predicts that there should be a gap at the charge neutrality point. So what I'm showing here is recent STM data from Ali Yazdani's group on devices and regions within those devices which show ultra-low strain. It turns out that the system is extremely sensitive to heterostrain, the difference between the strain of the top layer and the bottom layer. It turns out that it increases the narrow band quite dramatically. So when they look for regions which have very, very low strain, they discovered that the charge neutrality point is indeed gapped, which is what this strong coupling theory would predict. They, of course, also see the insulators at filling factor -2. And I'll come back to this in just a second. Okay, so now that we have our effective Hamiltonian, we found the exact ground states, we would like to find out what happens to the excitations. And what we will find out is that the excitations disperse, despite the fact that nominally we have no kinetic energy. In other words, in this problem, there's itineracy even though we are at strong coupling. And one way to show that is as follows. So imagine that omega, let's stay at charge neutrality point, where the argument is a little bit easier. So let's say that omega is the exact many-body eigenstate, which is annihilated by this density fluctuation operator. Now, let me act on this state with some operator x. So let's say x creates a particle or annihilates a particle, or it can create a particle and annihilate a particle, so it would be a charge-neutral operator. For that matter, it could be a trion operator, so let's say it creates two particles and annihilates one. X can be any operator that will fix with a fixed particle number. Okay, and so now let me act on this state that I just formed with the projected interaction. Now, because the density fluctuation operator annihilates omega, I can replace any product of this delta rho and x with its commutator. Of course, I can do that for the second product as well. What this means is that So let's say that this is one creation operator, and this, of course, contains one creation, one annihilation operator. The result of this commutation is just one commutation, one creation operator. I will not have a particle hole left behind. And the same thing is going to happen after the second commutator, which means that if I just have one creation operator on the right, yes, it can get moved around and superimposed at different positions, but I will not create a particle hole. And so then I can try to close this equation and solve for the eigenstates. And this is much, much easier than solving the full many-body problem. And what do you discover if you do this is that the excitation spectrum looks like this. This is a gap on top of the charge neutrality point. And the excitation disperses with the minimum at the gamma point and the effective bandwidth, which is itself set by the Coulomb interaction. LM here, remember, is the Moret scale. Now, this does not happen in a Hubbard model in strong coupling limit. If you were to turn off T in a Hubbard model and went to strong coupling limit, of course, you can find the exact ground state at half filling. But if you were to take one of these holes, if you were to take one of these particles away, so create a hole, this hole would just sit there. It would not disperse. Its band is completely flat. It also does not happen in quantum Hall. But here, the excitations actually disperse with the bandwidth which is not negligible. So as I mentioned, itineracy arises, or if you wish, emerges even at strong coupling. Now, you can extend this argument to the other integer filling factors. So now imagine that omega nu is the many-body eigenstate which, of the density fluctuation operator. Then every time you have a product of the density fluctuation operator and x, you can still replace it by a commutator and the density fluctuation operator acting to the right, but that's just a C number. And so as a result, the operator count on the left and the right-hand side of this equation is still going to be the same, and you still have a much, much easier problem to solve than so you don't have to solve the full many-body problem, and this is very easy to solve numerically with this additional term that appears over here. And you can think of this as giving rise to the exchange or the Fock part of the dispersion, and this as giving part to the Hartree. And now, if this is a creation operator, it will have one sign after the commutator. If this is an annihilation operator, it will have the opposite sign. And so this term will become important. Now, if we add these two together, in the special chiral limit, where this can all be done exactly, but it was checked even away from this chiral limit, the result holds qualitatively, you find the following. So let's go back to the charge neutrality point. There's a gap. And then if we add one particle or one hole, we discover that there's a minimum at the gamma point, and the band is fairly flat away from the gamma point, with the bandwidth set by the Coulomb interaction. Now, let's go to nu equal to 1. In this case, a Chern state is an exact eigenstate. And let's add a particle to this state. We discover something similar. It goes to the gamma point as a light particle. But if we were to add a hole, remarkably, it's extremely heavy. It's very, very flat. Similarly, and both of these, of course, are gapped excitations. Similarly, if we are at nu equal to 2, if we were to add a particle, it goes in as a light particle near the gamma point. But if we were to add a hole, now there's some dispersion to it, but the lowest energy hole is going to go into these flat regions. So they're heavy. Similarly, at nu equal to 3. And so you see, towards the charge neutrality point side, the excitations behave as heavy fermions. But on the away from the charge neutrality point side, the excitations behave as light fermions. And I'll come back to this in just a second. So this is the introduction. And now the question is, how do the strong coupling excitations behave in the presence of an external magnetic field? You saw how their dispersion came about, and the question is, do they Landau quantize in the presence of an external magnetic field? And particularly because the density operator is charge neutral, it's not immediately clear how the vector potential would couple to this problem. And so this is the problem I would like to address. So what we do know how to solve is the non-interacting problem in the presence of the magnetic field. There we know how to add the magnetic field. It's just a minimal substitution. You have Dirac particle in the presence of magnetic field plus the interlayer tunneling terms. And so one strategy which existed in the literature is just simply expand this in the lambda level basis. And you can do this, but this will be numerically prohibitive, particularly at low magnetic fields. And the reason for this is because the density of states in this narrow band is highly localized around the AA regions with a length scale which is, of course, itself set by the Moret length scale. But the lambda levels describe length scales at low field which are set by the magnetic length, which is much, much longer than that length scale. So if you want to build up this structure at shorter distances, you're going to need many, many lambda levels to do that. And as a result, you are stuck describing all of these remote bands, which you are not really interested in. At the end of the day, you would like to project onto this narrow band that splits up into Hofstadter subbands. So we would like to come up with a better technique that does this, projection. Now, so the key insight for this is to use the zero field hybrid Wannier states, which I showed you, to generate the finite field basis. Wow. So the key idea is to use Landau gauge. I thought I have 40 minutes.
It's 35 already.
Okay. All right. So, the key idea is to use the Landau gauge of the finite field. You take the state which we cheaply generated at zero field, and you take the one which is localized at the home unit cell, the unit cell where the vector potential changes sign. Now imagine you compute the expectation value of the finite field Hamiltonian with this state. Because this state is exponentially localized, exponentially small, far away from the origin, it will never pick up the large part of the vector potential where the x is large. And as a result, this particular state, even though it was constructed at zero magnetic field, will actually have to be a superposition of states from the Hofstadter spectrum at finite field. You can't escape to the higher energy bands. That's the key idea. Now, I'm not going to bore you with the technical details of how this works. In the interest of time, I will just show you what the result of the Landau quantization, of solving this problem at finite field is. So we now project these density fluctuation operators onto the finite field narrow bands, follow the double commutator trick, and compute the excitation spectrum. They're plotted as a function of magnetic field. These two panels describe the so-called chiral limit, and these two panels describe the more realistic case. So let's just focus on this one. You see this deep minimum at the gamma point, and indeed we find that those excitations Landau quantize. And over here in this region, which is very flat, we find that the Landau levels are very, very close together. So even though it was not completely obvious from the very beginning, indeed there is Landau quantization. We can compute the Landau level degeneracies and study the topology of these. This is the result at filling factor 2. Remember, the excitations on the away from the charge neutrality point side behaved as light fermions at the gamma point, and as heavy fermions on the away from the from the charge neutrality point side, they behave as light fermions. On the towards the charge neutrality point side, they behave as heavy fermions. And indeed, the light fermions have well-separated Landau levels, and so you would expect to see quantum oscillations and Landau fans from them. On the towards the charge neutrality point side, they do not. They're very, very close together, and you would be hard-pressed to see any quantum oscillations from this experimentally. And I think that this is a very natural explanation of the experiments that you have seen, namely that the Landau fans point away from the charge neutrality point side. Okay, so the part of the story that I do not have time to tell you about unless you ask me is how does this all connect to the topological heavy fermion picture advanced by Zhida Song and Andrei Bernevik. So let me just show you that this part can actually be solved to a large degree analytically. Very good. And this is the connection to, this is the last part I want to say. Since we can compute the lambda level degeneracies, the sequence that we find in this strong coupling limit is that at charge neutrality point, there is a gap, and this is a Chern number 0 state. The next one is a filling factor 2, so it's a Chern 2, and the next one would be 4. Now, interestingly, there are few devices which already were measured, particularly by Dima Yefetov's group, where they saw a gap at the charge neutrality point. And so that is consistent with our starting point. And they also measured the Landau fan coming out of the charge neutrality point. And indeed, they saw that the first stable one is indeed the filling factor 2. Now, it may still be a bit too early to claim victory here. And so what I think needs to be done as next check for this is the STM in the presence of finite magnetic field. And let me just flash my summary, and thank you for your attention.
For 1 or 2 short questions. I think Rachel is first.
Oskar, how does this compare with the topological heavy fermion model of Zhang and Bernavik?
Funny you should ask.
I won my $50.
So very quickly. Okay, so the picture that they introduced is the following. They want to think of, so focus on this inset here. They want to think about this narrow band as a hybridization between 2 fairly strongly localized P plus IP states and 2 Dirac cones, Dirac particles with the same winding number. There's a little bit of a splitting between them, so they actually have a quadratic band touching and the mass. And so in other words, they want to think about this as a topologically trivial band, flat band, which is flat simply because you don't hop between the triangle lattice sites, whose dispersion then arises entirely due to the hybridization to these topological fermions, whose winding number is 2. So that's how they built in the topology. It's not really a lattice model. It's a hybrid between a lattice, which are these flat band states, and basically a K dot P like dispersion. Okay, so the question is, how does one turn on a magnetic field on this problem? And this has not been answered until very, very recently. The idea is to use the same trick that I explained on the localized ones. In other words, we form hybrid Wannier states out of them, and then we project them onto the IREPs of the magnetic translation group. They will give us the correct count for them. And then the C fermions are easy. They're just K dot P. So the key question is, what is the hybridization between these 2 at finite field? It turns out that that problem can be solved. In fact, you can solve it analytically. And it reduces to, at charge neutrality point, to the following 6x6 problem. So this is a creation operator for lambda level. This is an annihilation operator for the lambda level. So this part, you see, is basically just a massless Dirac particle in the presence of magnetic field. So it's going to have a Landau fan like this. And it's going to have an anomalous level sitting over here. I already added the mean field interaction that they added. And then the heavy fermion part is just non-dispersing level, which is split by U1 over 2. U1 is the local repulsion. So if you don't couple the 2, the picture is going to look like this. The C's form Landau fan, and the F's, in their language, they just form this flat level here. Now, the key is to count them. So every one of these Landau levels has the number of states in these Landau level is set by the number of fluxes. But the number of states in the F's is the number of unit cells. And so that allows you to actually fully compute the Chern numbers of the resulting spectrum. Now, I'm not going to bother you with this. I just want to show you the result of this. So in this case, we're going to artificially turn off the coupling between the topological C fermions and the F fermions, which is what I just described. And now we turn on this coupling with 35%. Now you clearly see what's happening. They repel from each other. You form hybridization. And when you turn it on fully, you recover this lambda level spectrum. This is precisely what this is basically what you saw from the full projected calculation. They were bunching up at this high energy, but there was also a level which was sort of separated from everybody else at this low energy. And now we understand what it is. That level turns out to be the anomalous lambda level from the Dirac particles, from the topological Dirac particles. And this is the full spectrum that we obtained. Yeah, thank you very much.
All right. Now we have time for minus one short questions.
My question is, even without magnetic field, if you completely ignore the kinetic energy, if I understand it correctly, what do you think is the effect of putting it back?
Yeah,
in particular, the U4 symmetry, I imagine it might be broken by those effects.
Yeah, absolutely. It is. I unfortunately didn't have time to talk much about this. So you have this U4 manifold of states, which let's say a charge neutrality point starts out with say a valley polarized state, which you can then rotate in many different ways. There are also Chern states in that manifold. So it turns out that we know which state the kinetic energy selects out of that. It's a state in which you would like to make a superposition between the particles in two different valleys. There's a fairly easy, it's basically a super exchange argument. Although you're stuck in this ferromagnetic manifold, there's a sub-manifold of this, which you can kind of think of this as if it's antiferromagnetic. So it selects that state. It's an intervalley coherent state. And there's a name to this intervalley coherent state. It's called Kramer's intervalley coherent state. So for a while, theoretically, that was the expected state, both at the charge neutrality point and at filling factor 2. Now, this state is quite interesting because of the intervalley coherence, you may expect there is a Kekulé-like pattern you would see in STM. But it turns out if you do a careful calculation, there's a subtle interference effect in which at filling factor 2 and at filling factor 0, this Kekulé pattern will be actually absent from this state. There is another intervalley coherent state, which this calculation does not seem to favor, which does have this square root of 3 by square root of 3 pattern. The more recent STM data that Yazdani's group has done sees the pattern. So at this point, there's a debate on which terms, in addition to the kinetic energy, would stabilize that state out of the manifold. Phonons may be one of them. So it's still not completely sorted out, although the evidence seemed to point to the so-called time reversal invariant intervalley coherent state. Yeah, you're welcome.
All right, so I strongly suggest we move the remaining discussion to dinner. Thank you very much.
Thanks. Yeah.